This is the video for section 10.2, Calculus with Parametric Curves. So in the last section we talked about graphing parametric curves. Remember that these are curves that are defined by parametric equations, x equals f of t and y equals g of t, where t is the parameter. And in these, when you graph these equations for a certain range of t values, say t equals 0 to 1 or something like this, you'll get a curve, and that means that we can do all the things that we used to do with calculus for regular functions with these curves. So we'll be interested in finding the slope of the tangent line, so finding the derivatives, area under the curve, arc length, and surface area. So let's start with the derivatives. So fact is that so here's the formula for the slope of the tangent line. It's dy dx is dy dt divided by dx dt. And I'll rewrite this in a slightly different way in a minute, but I want to explain first how you get this from. This is just a different way of looking at the chain rule. And the chain rule says that dy dt can be written as dy dx times dx dt. And if you divide both sides by dx dt, then you get exactly the formula that I've written above. Okay? So, thinking in terms of the equations that we started with, here's my equation for y, and so I use that to rewrite the numerator here as g prime of t, and my x is given by f of t, so when I take its derivative, that denominator is f prime of t. Okay? I'm not going to do an example like this. We'll do one in class. You should look at examples number 1 and 2 in the textbook. Wow, that's a mess. Try that again. Examples number 1 and 2 in the text. In particular, this also shows how to find higher derivatives using versions of this in the chain rule. So that's derivatives. Area is a little bit more interesting, so I want to spend some more time with that. So if I have a curve that's being traced out exactly once, when I go in the range from alpha less than or equal to t less than or equal to beta, then the area under the curve, so this assumes that my y values are positive, are given by, so we would normally write this as the integral from x equals a to b of f of x dx, right? And this is another way, let's use a capital F here, where I'm looking at y equals f of x. This is another way of writing the integral from x equals a to b of y times dx. Now with the parametric equations that I have up above here, right, y is just g of t, and x is f of t. So if I want to compute dx, I would do just like if I have u equals f of t, I take the derivative of that function and I multiply by dt. And since everything is being given in terms of t, I need to change my x limits in the integral from x limits to t limits, and we end up with the formula integral t equals alpha to beta of, now I'm just going to put in my y equation, which is g of t, and my dx formula, which I computed over here on the right, as f prime of t dt. And what I want you to do is I want you to not memorize this last formula. I want you to memorize the technique that was used in order to find that formula. And I'll show you why with the following example. So let's look at the area. So here's an example. We want to find the area enclosed by the curves x equals t squared minus 2t, y equals square root of t, and the y-axis. Now, it is always really important to graph these curves before you start doing any sort of an area problem. And this example shows you why. So I'm interested in using the y-axis of one of the boundaries, and so in order to find the t limits for my parametric curve, I need to figure out where it intersects the y-axis. So the y-intercepts, those are given when x equals 0, so that says that t squared minus 2t is 0, and the t values I get are then t equals 0 and 2. And so the y values that I get here, when I plug in t equals 0, I get 0, and t equals 2, we get the square root of 2. And again, I'm using the parametric curve here in order to find my y values. Now that means that my curve is going to live in the positive above the x-axis from 0, 0 to 0 square root of 2. And since I have written out what the t values are for 0 and 2, let's plot one more point with t equals 1 in between. And when I do that, we get x equals negative 1 by using my x curve up above here. And I get, using my y value, that y equals the square root of 1, which is 1. Right, remember that t is my parameter, and I'm using t equals 1 here. And so that means that this extra point in the middle is corresponding to a point that's to the left of the y-axis, and my curve is somehow traced out in this direction. Now, in order to find the area between this curve and the y-axis, what I have to recognize is that the axis is on the right and the curve is on the left. So the area formula that I would use would be the integral from y equals 0 to the square root of 2 of, I have to take that right-hand curve minus the left-hand curve, and then integrating with respect to y because I'm trying to find this area. Now I'm going to do the same thing that I did on the previous page. I have an equation that I'm using for my x curve over here, and I have an equation that I'm using for my y piece in red. So my x that I'm going to use in this integral is t squared minus 2t. My y is square root of t, which is t to the 1/2. And then my dy I get by taking the derivative of this and multiplying by dt. My t values that I'm using, remember, are going from 0 to 2, and so when I plug into my area formula, we have the integral t equals 0 to 2 of, now I have to do minus x, so that's going to be minus t squared minus 2t times what I got for dy, which is 1/2 y to the minus 1/2 dt. And so we get the integral from, I'm just going to write this as 0 to 2 now, because those are my t values. Taking the negative of that difference just reverses the order, so we have 2t minus t squared. I'll bring the 1/2 out front, and that should of course be a t to the minus 1/2, not a y to the 1/2. So let's fix that. So t to the 1/2 dt. And now I'm just going to evaluate this integral. Multiplying that t to the 1/2 through the 2t minus t squared, we get 2t to the 3/2 minus t to the 5/2. Oof. That should be a t to the minus 1/2 there. So we get 2t to the 1/2 minus t to the 3/2 dt. And I integrate that. So 2, new exponent is t to the 3/2, so I multiply by 2/3 t to the 3/2 minus 2/5 t to the 5/2, evaluated from 0 to 2. So 1/2 4/3 times 2 to the 3/2 minus 2/5 2 to the 5/2. And if you simplify this, you get 8 square root of 2 over 15. The next topic we're interested in is arc length. And the book goes through and gives a very nice thorough derivation of this formula that I'm going to write. So we're going to assume again that the curve is traced out exactly once in the range alpha less than or equal to t less than or equal to beta. And I need to assume that the curve that I'm using, so x equals f of t, y equals g of t, have continuous derivatives. This is to just make sure that our arc length formula actually does what it says that it does. And now we can write out the arc length as the integral from alpha to beta square root of dx dt squared plus dy dt squared times dt, or if you like in terms of f and g, square root of f prime of t squared plus g prime of t squared dt. And this should look very similar to formulas that we had before for arc length, where we had 1 plus f prime squared, or 1 plus g prime squared. And using the notation that we had had previously, so this is what we call ds in this case, and this is ds in this case. And I'm not going to work out one of the arc-linked examples here. Maybe I'll do one of those in class. You should look at examples 4 through 5 in the textbook for examples like this. What I want to show you is how this works with with surface area. And so, if you recall, back when we were doing applications of integration, we looked at the area obtained by rotating a curve. And we looked at rotating the curve about usually the x-axis or the y-axis. So if we rotate about the x-axis, then we have that the corresponding surface area is the integral of 2 pi y ds. And remember that this was an extremely convenient formula for when we were looking at surface area previously. And it's worth noting here that we need to assume that y is greater than or equal to 0 in this situation. And so that's saying that the function g of t that we have parametrizing our curve has to be positive. If we rotate about the y-axis, then the formula we get is integral 2 pi x ds, here with the restriction that x is greater than or equal to 0. The text does an example for you of rotating about the x-axis, so I'll do one of us rotating about the y-axis. So this formula here will be the relevant one for the following example. So our example we're going to look at is we're going to look at the parametric curve x equals e to the t minus t and y equals 4e to the t over 2 in the range 0 less than or equal to t less than or equal to 1, and we're going to rotate that about the y-axis. So the formula we're going to use in the end is s equals the integral from t equals 0 to 1, so we're integrating in our range of t values. It's going to be 2 pi x ds. And we will use the equation here for x, and what we need to do over on the side is figure out what to put in for ds. And I'll work that through in some steps. So first of all, I need to take the derivative of the x function, which is going to be e to the t minus 1, no problem. The derivative of the y function is 2e to the t over 2. And now I need to square those and add them up. So we'll look at dx dt squared plus dy dt squared, and that is e to the t minus 1 squared plus 2e to the t over 2 squared. And I'll multiply that out to get e to the 2t minus 2e to the t plus 1 plus 4e to the t. So the first 3 bits here are coming from squaring this, and the last bit is coming from squaring this. And what I can do is to combine this bit with this bit in order to get e to the 2t plus 2e to the t plus 1. And if you remember back to when we did arc length and surface area formulas like this, you would get some nice cancellation that allowed you to rewrite the ds formula in terms of a perfect square. So in this example we have exactly e to the t plus 1 squared. So our ds formula is gotten by taking the square root of this and multiplying by dt. So we get exactly e to the t plus 1 dt for our ds. That's all the scratch work on the side that allows us to take inventory. Over here we now have the integral from 0 to 1 of 2 pi, put in that formula for x, and put in the formula that we have for ds. And now there may be a clever way to compute this integral. What I'm going to do is I'm going to pull out the 2 pi and then just multiply out the bits that we have in there. So e to the 2t minus te to the t plus e to the t minus t dt. And that's 2 pi will integrate piece by piece. 1/2 e to the 2t minus, no one has to do a little bit of integration by parts or to memorize this formula, but here we get t plus 1 e to the t plus e to the t minus 1/2 t squared, evaluated from 0 to 1. And if you work it out when you plug in t equals 0 and t equals 1, this simplifies down to 2 pi times 1/2 e squared minus e minus 1. So that's the actual surface area obtained by rotating that curve. Notice there's one thing that we need to check in order to make sure that this is valid. It's going to be totally cool, but we need to check that that x function that we used is greater than or equal to 0. If you look back on the previous page, that was the assumption that we made when I wrote out those two formulas. And so that's checking that e to the t minus t is greater than or equal to 0. And you can do that in a couple of ways. The easiest way for me to see is by looking at the graphs. So here's the curve y equals e to the t, and here's the curve y equals t. And since the e to the t curve is always above the t curve, their difference is always positive. And so we're okay with that. Right. So that's an example of the surface area computations, and this is the end of the video for section 10.2.